which is say based on a fixed prism. So this is common theory. So which, let's say we denote it in this fashion now. And I've not defined what it is, but as for example, you can keep them, let's say, A you could take to be a ZP. What do you want? And I is an ideal inside A, and that ideal would be just, let's take this one for now. Yeah. Bigger, okay. Thanks. All right, so so in here, this U minus P will be known as a distinguished element. Let me write it bigger. A is a ZP double bracket U, so it's the completion of. Okay. Sorry? Oh, press the chalk. It's not bold enough, is it? Okay. Let's try enlarging first. So. Not bad. Okay. And the ideal would be, say, SP. Okay. All right. So let's just, and this one would be known as this distinguished element. We'll define them. And you have seen this kind of distinguished element. Which precisely will mean that there will be a delta, the p derivation, we should take this one to an unit, and there will be some extra conditions which makes it a prism. So this ideal is already principal. So you have that. Then, then this is this. Then these various comparison theorems actually come out of this cohomology theory. So let me just write it. So let say MRI. And I'll throw in an undefined term here, which we'll see at the end what it means. So this is the derived object. It's represented by a chain complex whose cohomologies are what we are interested at. So this will be denoted like this. So X is our formal scheme, and it's this A is the base prism, which is fixed. And you have this derived object, and this would be defined to be the right derived of okay, so over here, again, this would be the prismatic site. So this is something that we'll see today. And this would be what's known as a structure sheaf on this side. And you take the right derived functor of the sheaf of the functor of global sections for this sheaf, and you get this complex. And out of this complex, you build out, basically it throws out these comparison results. For instance, one instance is the crystalline comparison. That okay, so in this particular case, you take I this fixed I to be, let's say, generated by P, which in a way you can think of it that you set U to be 0 actually in this particular instance. Okay, then there exists a canonical phi equivalent Okay, so the left-hand side is, again, it's done by the usual, you take the crystalline site and you do a very similar business and you have the crystalline cohomology, or whatever the chain complex has to do with that. And here, you have this R gamma out of this crystalline site, but you take a phi twist of that. Now, how is this, so where is the phi? The way these things will be defined, actually, at the level of sites, there will be an action of the Frobenius. There will be a Frobenius lift. So as a consequence, the cohomologies will naturally, all the chain complexes in the derived objects will have a Frobenius action on it. So what it says is that this is isomorphic by a phi twist of this thing, actually. So that's the first comparison. And then I want to, maybe I won't write down, maybe why not, actually. The other comparison, for instance, is the Derham complex. So again, there exists a canonical so again, this is the Derham chain complex, which is over A over I, because our objects are defined over A mod I. So for instance, in this case, it would be over, say, ZP. And so, yeah, the Derham chain complex would be over A mod I. And that, but then these guys are actually defined over A, this thickened base, this prism. So this is, I'll just put the word up here so that we get used to this. So it's a prism. So in a way, these things are all kind of A modules. But this is an A mod I module, so how do you obtain the A module? A module, so that is yeah, okay. And then this is a derived thing. So morally, you have an object over A, if you base change it over I, but with a phi twist, actually. So yeah, so this is exactly like, you treat A mod I as you precompose it with the Frobenius, and if you have the phi twist, and then if you base change in the derived sense, then you get the Derham cohomology. So that's the second kind of result. So it's sorry. This is the usual Derham cohomology. You can take the hypercohomology, the spectral sequence or something, which is over A mod I. Yeah. But is the usual algebraic Derham complex won't work, you're saying? Yeah, but they are they can be treated as a system of schemes, right?
Yeah, but their CPOP intensive can be unique.
Yeah, but I think you don't take the limit. You pass to the limit at every stage. Actually, you don't. So these things are defined over some nilpotent, where P is nilpotent, and then exactly. Yeah, you don't go to the limit and then look at that. You to get the limit at every. Yeah. No, this is the prismatic cohomology. So that's the comparison, that you can get the Derham cohomology from the prismatic via base change. Okay, and then let me stop with writing undefined things. But then, of course, there is another the Ital comparison is also obtained as follows. Okay, but let me not write anything there. So you can, yeah. It's the right direction, right? Okay. Sorry if I hurt someone's feelings. All right. Okay. All right. So, so today, so yeah, one of the kind of the principles of kind of the moral philosophy of this cohomology is that you kind of obtain various cohomology theories via kind of restricting on this kind of a two-dimensional object. So in a way, the picture that kind of is is going around is basically that, for instance, the crystalline kind of corresponds to, let's say this is the u direction, and this is the p-adic direction. Say this is the zp direction in this two-dimensional object. Kind of u equals to 0 kind of gives you the crystalline cohomology. So you drop down to zp and this thing. The DRAM kind of it is in fact, if you look at this, just look at this as a divisor, u minus p, and then but of course there is a Frobenius twist actually. You kind of have to twist it by the Frobenius. Here the Frobenius, in this particular case, you will, let's say we fix this one. So for the DRAM case, in fact, you really are restricting along, say, UT. I'll probably get it wrong. So, but the morally basically is you kind of restrict this along this divisor actually. Base changing along this divisor, but with the Frobenius twist. That will give you the DRAM. And the Ital comparison is something that morally it says that if you look at kind of the generic point, you kind of look at the complement of this divisor where p is 0, and you base change. You kind of look at the restricted on this open kind of set, then you get the Ital comparison. This is I hope I got this right. That's kind of the principle actually. So to tie it up with what's going on in this workshop is that the DRAM, I didn't write anything because I didn't want to throw in any. If you want, I can write it actually. Yeah.
You're going to say where you're looking at the first one.
No, because the symbols won't even give you any clue. Like over here, the symbols still kind of you can make sense of restricting. But yeah. Okay. So just to tie in with what we are doing in this workshop is that you have seen in these lectures of p-adic Haus theory that the DRAM, so combining the DRAM and the crystalline, I mean, you are looking at vector spaces with a filtration, at the same time a semilinear operator, right? And then using these various period rings, you tie it with Galois representations. So which is the Ital? Well, the Ital cohomology is a Galois representation. And there are various comparison results that ties in DRAM with crystalline, DRAM with Ital. This prismatic cohomology is basically kind of the mother of it's like the mother of all the cohomology theories, and you can kind of derive whatever you want actually as long as you're specializing correctly. So okay, so that's kind of the philosophical note. Okay, so today we want to kind of at least see what this prismatic site is. And maybe tomorrow we would like to actually see how this crystalline comparison happens actually. So tomorrow, hopefully if time permits, the crystalline comparison. So, and the principle is very nice and elementary. The principle is that, so you have seen in one of the lectures that the crystalline cohomology, the sites are defined by these PD thickenings. So these divided power structures, that you define the sites as using those divided power structures. So you have these PD structures. The insight is that you have seen delta rings. The insight is that these PD structures can be recovered from delta rings. And it is very elementary. It's just playing around. So in that way, it's accessible, but at the same time, I at least right now don't understand what's going on in a real sense. Okay, so that's the, let's hope we can get there. Okay. So let's try to approach prismatic site today. So yeah. The ETL comparison? Yeah. Okay. I'll do it. No, that's okay. I'll do it. Just have to copy it. That's all. So okay. So in this particular case, you assume A is perfect. So it's a perfect prism. Okay, so you have seen how to construct these adic spaces. So you have a formal scheme, and there's this Raynaud functor to you kind of tensor it over QP, and you get an adic space. So it's, yeah. So x eta is that. So this is what it's an adic space. Okay, so for okay, so that's yeah. This is your whatever the ETL cohomology, and this is somehow obtained by so the Frobenius. If you fix it to, I mean, if you look at the one component of the Frobenius, and then that symbol, I don't know what it means, 1 over I, but okay, yeah. X is defined over A mod I. So example A could be this. A could be A inf actually, that no, that is a generic fiber. I mean, X is over, say, I mean, if it's over ZP, actually, you look at the coordinate ring of, say, let's say X is affine. You look at the, I mean, there's a way of, if you have a formal scheme, you attach an adic space by the Raynaud functor. So that's what that X eta is. It's a rigid space. A is, so in this case it's not, but it's perfect means that its Frobenius is an isomorphism. So let's just recall that. So a delta ring is a pair. So A is a commutative ring, and it's a pair. So you have seen this, for instance, in Jim's talk. Just recall this, and it has this Leibniz rule. So this is. It satisfies this. And again, you saw it in Jim's talk that this giving a delta pair is equivalent to actually giving a ring homomorphism. So giving this data is equivalent to giving a ring homomorphism from A to the p-typical Witt vectors of length 2. And this is again, if it's length 2, it's denoted with 1. Okay. So the entire information is encoded in this. All right. Now, for instance, okay, so now, see some examples. If you take Z localized at P, there's a unique delta structure, which is simply given by x minus x to the power P over P. And with associated with these delta structures, you have seen that there is an associated Frobenius. Here, the Frobenius is the identity. And yeah, so let me set this up. We'll need this tomorrow. So secondly, that you've seen the jet spaces. I'll use different notations, but I'll reconcile with the notations used in Bhatt and Scholze's paper and notes. So take for an example, A to be, let's do it over, say, Z localized at P, X over F. Now over here, X treated to be a bunch of variables, actually. One variable is fine, but treated to be a bunch of variables, and F to be also a bunch of polynomials. So just writing a shorthand, actually. So, okay, so then, localized at P. Yeah. Yeah. All right, so this ring, which Jim was denoting it to be this lambda or delta, what are you using? Delta. VM writes it like this. Sorry. This one, in this, if you have a description of A to be that, so then what you do is that X, and then you adjoin these new variables. No. It's just X. Because X is actually, the identity is the lift of Frobenius. Yeah. And this is also always divisible by P by, let's say, Farmer's little theorem. So it all works out fine. Okay. So you adjoin an infinite set of variables like this, and this delta compose Nx is a variable. And just to again reconcile with the entire literature that's there in this arithmetic jet space theory, this is generally denoted as this. So I'm suppressing these notations. I'll just keep these for now. And quotient it out by F, and then take delta of F and delta square of F, and it's the usual thing that you expect. And I'll write an example in which it will be clear what it should be. Instead of me describing what it is. So let's just see a quick example. Let's say A is so this actually the coordinate ring for two-axis meeting. Then if you want to then construct this J infinity of A, then what you simply do is that you adjoin new variables. And then keep doing that. And let's just compute the first two polynomials that one should coefficient out. First one would be this f, which is xy. And the next one would be delta of xy. Second would be delta square of xy. And how do you compute out delta of xy? Well, you just use these rules to FOIL out this expression. So that would be delta of xy. If you use this rule, it would be x delta of y plus y delta of x plus p delta x delta y. And you keep doing this process recursively for any delta n applied to this. Sorry? Yes, p powers. Thank you. X to the p, y to the p. Next. All right, so that's an example, and that's how it's a formal thing. And so this is the infinite jet ring, actually. Okay, and actually, I mean, since you mentioned this, I mean, I don't know whether I should. Yeah, I mean, that left adjoint property is this universal property for J. Yeah, so the lower, when these indices are in the lower, means that these are rings, actually. If I ever happen to write something on top, the superscript, that would mean the space. But I don't think I'll do it, actually. So, so the universal property, which was, as Jim mentioned it, it was the left adjoint property of the forget-root functor. It translates as follows. I won't write down the whole, I'll just write. So J infinity of A, then there is obviously a natural map from A to J infinity of A. You just take the image of, let's say A is given by the description, Zp of x modeled by some f. You just look at its natural image inside this J infinity of A, which is freely generated by these various operations, actually, or generated out of these operations. So, so you have this natural map U, and suppose you are given a map F to another B, which has a delta structure, which means there is a delta on it. So given any map like this, then there exists a unique map from J infinity of A to B, such that, well, the natural thing is that, okay, if you go F, that should be the same as going U and then G. And then second thing is that if you are here, and J infinity of N acquires a natural delta structure. And that is actually very easy to see from this description, right? It is induced from, if you have a symbol here, let's say it is delta composed nx. If you want, the delta structure is induced by, if you hit this with a delta, it should be delta composed n plus 1 of x. So that delta structure, yeah, on this, yeah, you can see it factors through the ideal, and everything is fine. So, so hence this acquires a delta structure. So this is a fixed data, and given any b, if you go by delta on J infinity of A and then G, that is the same as first going to B and then apply delta. So this is delta composed G. It's, going first G and then delta. Okay. So you saw this. I thought of again reminding you again. For the Witt vectors, the arrows were the other way. So. All right, let me now quickly, I don't think I have, so this is a remark, and okay, I won't prove this lemma, but the remark should be good enough then. I think. Yeah. Okay, the remark is that the delta So delta doesn't behave well with localizations. For instance, let's say you start with a delta ring A. This is a delta ring. And let's say you invert X in there. Okay, so let's say you invert X. Then you need to compute what is delta of 1 over X in this new ring, right? Invert X and you get, say, A prime, where X, you look at the multiplicative set, a monoid generated by X, and look at A prime. Then what, you want to really see that what delta of 1 over X looks like. Well, how would you compute it? Well, 1 is X times 1 over X. And then you hit the entire thing with delta. So you get delta of 1, which would be 0, will be delta of X times 1 over X. And well, now use those rules, which I've erased. Now it's over there. From there, you will actually get the delta of 1 over X. I'll just write the final form. It will be this. Maybe with a minus. Okay. So if you apply the laws over there, you'll get delta of 1 over X is minus delta of X over X to the power P times phi of X. So now you see, it's not, I mean, if you're just inverting X, it wants that you also invert phi of X. So that's the statement that it does not localize very well with if you I mean, if you're on an open set and you're kind of looking at a smaller open set, say given by localization, then it might not preserve the coordinate ring. However, if A is p-adically complete, if A is p-adically complete, then you could do this. So then this form. Now, phi of X, well, that is this one. And then you can pull out an X to the power P. And now this one is invertible, actually. So this you can, this is an invertible element, actually. It's whatever, it's 1 minus, so it's a unit, basically. So, then this is convergent, actually, in that new ring, p-adically completed. And so then everything is restored. And this is kind of relevant in the construction of jet spaces, actually, over p-adically over p-adic formal schemes. Okay, so this is a lemma that this is to motivate this lemma that this is not hard to prove, but this is just to motivate this condition that if you have a multiplicative subset of A, you need this extra condition that phi of S is inside, it preserves S. Then this S inverse A admits a unique delta structure. Okay. Okay. So now let me define distinguished elements. When you're assuming this, no. Because you see in the formula, it's all fine, because delta of 1 over x is minus delta x over x to the power p, and phi is in there. Okay. Oh, a definition. Okay, so, and so you declare an element D to be distinguished if delta of D is a unit. So let's see a couple of examples. So yeah, first example would be A is ZP and D is P. Then you can see the delta of D, well, it is just, well, the Frobenius is an identity here, so but let me just compute it. Right, so we are using this. If your ring has no p torsion, actually, then delta of x can be computed as, if you recall from Jim's talk. And okay, phi is identity, so this is exactly p minus p to the power p divided by p, that is 1 minus p to the power p minus 1. And that is an invertible element in ZP. Okay. Okay, that's one example. Let's do this other one. This is sometimes written as PQ. Okay. Yeah, so this is a and on this one, the Frobenius is induced by phi of q going to q to the power p. Oh, A is a q minus 1 adic completion of CP of q. All right, so yeah, so this is related to this q Dirac situation, which we won't talk about, but the example, at least, is a nice example. So, okay, so here the claim is that the delta, the D, is distinguished. And one can directly actually compute. I mean, this is well, it's a sum. You hit it with delta and just prove that actually this is distinguished. Or actually, let's. Yeah, so okay, so this so you look at the reduction mod q minus 1 map to ZP, and one can check that actually is anything here is invertible if and only if its image in here is invertible. Actually. Now, and let's actually use that fact. So let's call this, let's say, pi. Okay. Then note that actually that pi is in fact is a delta map also. Yeah, yeah. So it just sends q to 1. So delta map. So pi is a delta map, which means what? If you, so both of these guys have delta structures. ZP we just saw, and this guy has a delta structure induced from this. Then pi commutes with that. If you go delta here and then pi is the same as the other way. Having that, using that, so okay, now let's just rewrite D. This we can rewrite as P plus, we just throw in one. So this is a, I just wrote D like this. But then this precisely means that this is in fact P plus Q minus 1 times some H. Okay? And now we want to really know what delta of D is. But now let's just see what happens if I hit it with pi. But then since pi is a delta map, so then it will just do that. And then here it becomes much easier because pi of D, well, this entire thing goes to 0. So all I have to compute is delta of pi, delta of P. Mod, well, this is in ZP, so I don't have to take a one. This is in ZP. And this one we just computed. This is 1 over 1 minus P, which is a unit. Okay, that's one example. That, and another example is this one. You have seen it. Let's say a couple of many talks actually. For instance, Kiran's talk, and this is the AINF thing. So another third example is so. You have a perfectoid field over QP, and you take the AINF of, and then you take an D of the tilt. That's how you write it. But generally, sometimes it's written just AINF of OC also, right?
But it doesn't matter, right? Characteristic E or S inverse.
Yeah.
Characteristic E object.
Yeah. Yeah, if you write it as the inverse limit of the Frobenius. Yeah. Yeah. Okay, but with the standing notations, that's how it's written. So, okay, so yeah, and D is in the kernel of this theta map. So if you take any generator of this kernel, that turns out to be a distinguishing element. So this is from. It's a generator, so. Okay. Okay, so if, again, a delta ring and D in A distinguished and U in A star, it's a unit. Yeah, it's sort of habit. Yeah, so, okay. D, thanks. Okay. So if D and P both belong to the radical, actually, so of A, then U times D is distinguished. No, the Jacobson radical. Okay, so so I'll prove like a couple of very simple lemmas. The reason is to build up to one another bigger lemma or whatever. So okay, so but these are very direct. There's nothing much to do. So you really want to check delta of U. D is a unit. Again, you apply those laws. You get this. units, right? Okay. This one is a unit. U is a unit, delta of D is a unit. And this one belongs to the radical. Yeah. D belongs to a radical, P belongs to a radical. So you have an element which is a unit plus a radical, so hence it's a unit. This is it. So all right, the next one. Do you have a star? Okay. All right, so again, the A is a delta ring, D is a distinguished element, I won't write that. So, okay, assume that you can write your distinguished element, D, so carrying the same notations, D is a distinguished element. D, you can write it as follows, F times H, where F and H are in A, so that both of them are in the radical, actually. Okay. Maybe I should have written the first place. Something's funny. Sorry. Yeah. Okay, so yeah, you write D as F times H such that F is in the radical and you want P to be in the radical. Then F is distinguished and H is a unit. So you see the trend actually that the distinguished elements, they should be in the radical. And P also should be in the radical. So, okay, so it's also a quick thing. 2 minutes, okay. Let me just quickly, so this is in fact, this can be foiled out. That's, the laws actually could be, this last two terms could be grouped and in fact written as this actually. Phi of H times delta of F. And this one is in the radical of A. And this one, no, sorry, I have to write the whole thing out. Okay, so this one is delta of F plus so we have that, and then yeah, so then this is in the radical. And this one is in A star, by definition. So which means that H to the power P times delta F is a unit, because, yes, yeah. And that proves both the statements, actually. I don't think the primitives that we saw, I think they are distinguished elements. Isn't that? Generators of the ideal. Yes, yeah, they will be distinguished elements, yeah.
So, are there distinguished elements that are not primitive?
No, I think they're the same. That's what I think that's the notion, yeah. That any element that's generating the ideal is a primitive, actually. Is a distinguished element, yeah.
No, converse.
The converse.
Every distinguished element coming from such.
No, not in A-inf, actually. No,
Okay.
Not in A. Yeah. But if you complete it with respect to that, with respect to the kernel, then I think that's true, actually. Okay, I think I have to stop here. So maybe, okay, so next, tomorrow. Tomorrow we'll actually define the prismatic site and then see some elements about that, the comparison theory. Okay, I'll stop here. Thanks.